So here are the first set of due dates. So after today, you're going to be able to do these first sections. So I'm going to make those due on Friday, the first section. And then the other two sections of this top one will be due on Tuesday, but you won't be able to do them yet today. So that's all the due dates I have so far. What I want to do today, so last time we did the electrostatic station, so you got to see some examples of static electricity. And what I want to do is I want to kind of formalize that and get it into a form that we can start to explore a little bit further. So that's what we're going to do today. And then, like I said, after today, you'll be able to do these questions about Coulomb's law here. Let me see here. What else I have to say about this? So homework wise, right? Make sure that you don't forget about your final exam review. And remember the bonus that's attached to that. Last day for makeup work is going to be this or next Friday. So don't give me any makeup work on final exam week. And then, like I said, we can now do that first section on the syllabus. As far as test questions go, my goal was to be able to do them today. Your class is graded, but yours is the only class that's graded. So I'm actually bumping test corrections. Okay. Go ahead and get out your notes. Yeah. What's that? Oh, yeah. So you can label your notes for today electrostatics. This is electrostatics. I mean, you've heard of static electricity before, but I think this was one of the questions in the package you did. But does anybody remember what's called electrostatics? Electrostatics right now. What's what makes electricity static? Or if it moves, or if it does move, it moves like through a spark once, right? That's different than you plug something into the wall, right? We'll eventually get to. But if you plug something into the wall, the electricity is continuously moving, right? Before we get to that, we got to talk about electrostatics, which again, I'm going to say it's the study of charges that are stationary. And then when I talk about charge, I want to give you a definition of charge. And this was one, it was a question on, I think it was station 1, that the book actually didn't do a good job. It gave you this thing called charge, but it didn't do a good job of defining it. The reason it didn't do a good job of defining it is because it's a very hard thing to define. A charge is a charge. It's like saying, I'm trying to think of another example. It's like saying color, right? Something is red. What do you mean it's red? Well, it's red. That's what it's like. I mean, yes, it's a color. Yeah, we could go into more depth on that, but charge you actually can't really go into more depth. That charge is just it's a thing that is, right? So what I'm going to say, the way I'm actually going to define it is it's a fundamental property. When I say fundamental, it means that you can't break it down into anything simpler, but it's a fundamental property of matter that allows it to, fundamental property of matter that allows it to experience an electric force. So things that have charge experience electric forces. Things that don't have charge don't. Probably already aware that there are two types of charges, right? There's positive and negative. But you learn, but one of those stations you saw, which one of them can move? The positive and negative. Negatives can move, and why is it the negatives that move? Yeah, if you think about an atom, right? Where is the positive? The positive is the middle, right? The electrons are on the outside. Now, someone said, I think Soltis, you said something about ions. You actually can get, there are situations where you can get positive ions to move. But for the most part, we're talking about just electrons that are moving in. The electrons that are moving, they're the ones that are on the outside of the atom. It turns out that the reason why electrons are negative is because one of the early people to do research on electricity was Ben Franklin, right? And Ben Franklin didn't have any idea about electrons, and so he just had to pick one charge to call positive. And he picked the wrong one because it turns out that again, it's more often it's negatives that move. But Ben Franklin picked positives, like he picked them backwards. So a lot of times you're going to find things that seem to be backwards because the things that actually carry charge, the electrons, are negative. So sometimes things are backwards, and that's just Ben Franklin guessed wrong. Yeah.
For one,
Yeah.
like, it's like the trying to keep thing, is that like a myth or is that like a real thing?
It's a fact. It's a real thing. Yeah. Do you guys know I'm taking cheaper? I think it's what's that? Sure. Yes. Well, protons and electrons, right? So where the charge resides in matter is in the protons and electrons. Yeah. But yeah, I'm pretty sure, Leo. I think it's real, but you're right. It does sound like one of those things that could have been fake story, but. Okay, so here's what I want to do. I want to talk about because Sohaib asked this question: are charges just protons and electrons? Yes, they are. So yeah, go ahead.
Okay, so it did happen, but it was not struck by lightning. So
It wasn't struck by lightning. So what happened?
because that would have electrocuted. So it picked up negative charges from the storm. It just wasn't struck by lightning.
Oh, so it just
Probably with that status of-
okay. Was in and did he feel it or did he have it like grounded or something?
Yes. it did.
He felt it. Okay, interesting. Yeah.
I'm pretty sure he had like the feet at the end and he had like a claw at the end.
Okay. So I guess it didn't get struck. I'm gonna have to do some reading up on this. This is interesting. So I want to talk about when we talk about charge, right? And this kind of goes to Sohaib's question. But there are two ways to think about charge. There's what I'm going to call the conventional model, which is Ben Franklin's model, and it's the model that is. So most of the study of electricity happened before we knew about atoms, right? So so what I'm going to talk about is I'm going to talk about charge in two ways. I'm going to talk about the conventional model, and when I say it's conventional model, this was before we knew what it was. It's how we thought of things, and so because of inertia, that's how we started thinking about things, and so it's still how a lot of this is thought about. And then there's a real model, which I'm going to call the atomic charge model. And so the conventional model is that things that are neutrally charged are neutrally charged. So here's an object. So things that are neutrally charged because there are just as many positive and negative charges. So I'm going to draw 5 positive charges in here. And I'm going to draw 5 negatives. And this is neutrally charged because they cancel out, right? In the atomic charge model, at least at this level, it's not too different, right? So what's really happening, what we're saying now, what's really happening is you've got this object, and what they really have is you've got these atoms, and I'm going to draw a very, very simplified model of an atom. So I'm going to draw an atom as a one positive charge that's the nucleus, and one negative charge that's the electron. Now, there are more protons and there are more electrons, but just for a simplicity's sake, I'm going to draw again 1, 2, 3, 4, 5 protons, and I'm going to say that they each have 1 electron around them. And I'm drawing the electron as orbiting the proton. Again, this is simplified, but it's more true, right? So this is what so this is the conventional model. The conventional model is positive negatives are just charges that like float around in an object. And then the atomic charge model says that, well, what they really are is they're the protons and electrons in the atoms, right? So they're not very different yet, but then I want to show you what happens, right? So in the conventional charge model, if you bring something near a positive charge, right, it's gonna what's gonna happen is this positive charge is gonna push. So positive and positive repel, right? So this positive charge is gonna push all of these positives to the opposite side of the object, and it's gonna attract all the negatives to this side of the object. So this is what happens in the conventional model. In the conventional model, you bring a positive charge near to it, and it's going to pull all the negatives one direction. It's going to push all the positives another direction. Okay? Now, what's quote unquote really happening, right, is the atomic charge model here. What actually happens is if I bring a positively charged object next to this, what actually happens is the atoms don't move, right? So the positive charges don't move. And what happens is all of the electrons, so the electrons can move. So all of the electrons end up like being pushed over here to, so 1, 2, 3, 4, 5. But I want you to realize here, right, the difference. It's a subtle difference, but in the conventional model, which works, it will show the same thing, but it's not actually really what's happening. So in the conventional model, you think about negative and positive as both being able to move. But what really happens, and that's what this station was trying to show you, right? What really happens is that the protons, the nucleus of the atom, stay put. The electrons are allowed to move, and so what happens is if these electrons are allowed to move, the same thing happens, which is you end up with one side of your object that's negatively charged, and you end up with another side that's positively charged. So a lot of times we will use this as a shortcut because this still describes on net all the negatives end up over here, all the positives end up over here. But just know that in reality, it's not that the positives and negatives are moving. It's that the positives are staying put and the negatives are going to the other side. Okay, that makes sense. Okay, but charge is this fundamental property, and it's the fundamental property specifically of protons and electrons that cause this thing to happen. All right, I'm going to give you another couple definitions here. I'm going to talk about grounding, or if you are British, you will refer to this as earthing. So sometimes if you read this, they'll talk about something being earthed. So generally, the American English way of talking about this is grounding. So grounding, if something is grounded, right? What that literally means is that it's attached to the ground somewhere. Okay. So in a plug, you will know what the grounding problem of the plug is. the third one. It's mine's backwards, but it's that third, you know how some things have two outlets, some things have three. That third one, that's the grounding plug. And what that literally does, at some point, that wire, a lot of times it will get like either connected to a water pipe or something, or sometimes it will actually get put into like a stake that's literally driven into the ground. But the idea is that if something is grounded, it's attached to the earth. Now, why do you want to do that? The reason why is from an electricity perspective. What does a ground do? A ground is a reservoir of charge. When I say reservoir of charge, right, what I mean is that it's so big, it's got so many positive and negative charges. So the ground is nuclear charged, but it's so many positive or negative charges that it's like taking buckets out of the ocean, right? So the ocean is like a reservoir of water, right? Or even a reservoir, right? Or so an actual reservoir is a lake, right? That's been made with like you dammed up a river, it backs up and it makes a reservoir of water, right? The idea of a reservoir is you can take a bucket of water out of a reservoir, and yeah, you took water out of the reservoir, but considering the total amount of water that there is, like you didn't actually make the level of water go down, right? There's so much that it doesn't respond to like little buckets of water. That's what we mean by the ground. The ground is a reservoir of charge. It's got so many different positive and negative charges on it that I can take charges out of the ground, or I can put charges into the ground, and the ground doesn't care. It's so gigantic, right? So the reason why you talk about this, and you talk about, you've probably heard this idea before that electricity wants to get to ground. Why does electricity want to get to ground? Well, so think about this station now. So the station over here was the Van de Graaff generator, right? So if you got so if you were up there and you charged yourself up with the Van de Graaff generator, and then you touched somebody else, right? There was a spark. Why was there a spark? What's that? They want to move away from each other, and they want to get to the ground. Okay, so the idea is if you got so the Van de Graaff generator, let's say that it has a positive charge, right? Let's think about this in terms of conventional charge for a second. Let's say the Van de Graaff generator has a positive charge. If you touch it and you get a bunch of positive charges on you, right? Positive charges want to repel each other, so they want to get as far apart from each other as possible. You can't get any farther than like a reservoir, because a reservoir means that the positive charges can get as far apart from each other as they ever could want to be, right? So the idea of electricity wanting to get to ground is that if you have a certain charge, right, all those charges want to repel each other, and so the farthest they can get from each other is by going to the ground. Okay. I want to talk about this in a little bit more of I want to talk about this by talking about how to charge things. So I know it seems like I'm going on, but once I talk about this, it's gonna make more sense about this. Anybody remember there were 3 ways, depending upon where you looked in the book, it was either 2 or 3 ways to charge things. Do you remember any of them? Yeah, so charging by friction. So there's charging by friction. What else? What's that? Charging by induction. And there was a third one. Conduction, or I call it contact. Yeah, charging by contact. I'm going to talk about each of these, right? Yes. Yeah. Yes. Give me 2 minutes. That's where I'm gonna kind of explain that a little bit, but I gotta talk about these charging, and then I think I'll make sense after that. Yeah.
Both people on like the plastic stools, so both of them have it, there's still be spark.
That's a good question. So if you had a perfect ground, there would still be a spark, but it wouldn't be as strong. Because in essence, what you'd be doing is you'd be taking the charge that one of you has and distributing it across two of you, instead of taking the charge you have and draining it all over the ground. You drain half your charge instead of all your charge. Yeah.
If we were to take like an object and charge it,
Mhm.
right, and then before it touches the ground or gets in space, would it, if we came back with 100 years later, would it still have a charge?
In space, yes. So the reason things lose charge on Earth is, so the reason why if you were able to like not touch anyone or something for long enough with the Van de Graaff generator, eventually the charge would drain. And the reason it drains is because of the humidity in the air. So it will drain eventually to the ground through the humidity in the air, but it will do it rather slowly. But that's where when things lose their charge, it's because of usually to the humidity or something. But if you really had a vacuum, yeah, there wouldn't be anywhere for that charge to go. Okay, let me talk about these three real quick, and then I think this will make more sense out of what a grounding is once I talk about each of them. So charging by friction, where did you charge things by friction? When were you charging things by friction? When you were rubbing the rods, right? You're rubbing the rods, and what does that mean, charging by friction? So if you think about what this physically is, right? What physically happens is you rub the rods with that cloth, and what is that cloth doing? It's ripping electrons off of the rod, right? Or sometimes the rod, it depends upon which one wants the electrons more. So depending upon which material it is, it's either that the rod is ripping electrons off the cloth, or the cloth is ripping electrons off the rod. But either way, what happens is one gets a negative charge, the other gets a positive charge, right? That's what happens there. That's charging by friction. Charging by friction is different than charging by contact. Where was an example of being charged by contact? Van de Graaff was being charged by contact. If the Van de Graaff had a charge, right, and you touched it, you weren't rubbing the Van de Graaff, right? So you weren't getting the charge by friction. You were getting the charge by contact, right? Because it was charged, you touched it, and then some of the charge came to you, right? As opposed to when you're rubbing something, there was no charge, and the friction made the charge, right? The friction separated the positive and the negative. Over here, what happened was the Van de Graaff had a positive charge, and by you touching it, you got that positive charge, right? The most interesting one is charging by induction. And the key about charging by induction is that you can charge something without touching it, but that thing has to be grounded. And this is where I'd like to talk about the Van de Graaff a little bit more. So I'm going to draw a little bit of a diagram here. So we're going to imagine, so here's your Van de Graaff generator on table. Okay. And I'm just going to imagine for a second, let's say that you are standing on the ground. So let me draw the ground here. You're standing on the ground and you're getting ready to touch the Van de Graaff generator. But you haven't touched it yet, right? I don't know if you noticed, but some of them, like if you were close to the Van de Graaff generator, you might have been feeling the electricity even if you weren't touching it. So even if you were the person running the drill, right, you might have still felt a little bit of that of the electricity. So what's happening here, right? So what's happening here is, again, the Van de Graaff generator, through a complex, we could talk about how the Van de Graaff generator works, but right now we're just going to say that magically the Van de Graaff generator makes itself have a positive charge. So I'm going to draw a bunch of positive charges on the Van de Graaff generator, right? So what does that do? What that does is, if you are standing on the ground, so let's imagine for a second you're not on the stool, you're just standing on the ground. What's going to happen, right, is as you get closer and closer to the Van de Graaff generator, you are on the ground, so you are attached to that reservoir of charge, right? So you're attached to basically an infinite amount of positive and negative charges. What's going to happen if you get a positive charge wants to attract which kind of charge? Negative. Positive charges want to attract negative charges. Since you're on the ground, which is a reservoir of charge, you pull negative charges off the ground, and the negative charges get pulled off the ground onto you. So you actually become, by induction, you become negatively charged, right? So the Van de Graaff is positively charged. As you get close to it, you become negatively charged. So Leo, this is the answer to your question, right? So it's actually before you touch it, you're negatively charged, right? Why does the spark happen? The spark happens because all of a sudden, right, you've got this positively charged Van de Graaff generator, and you're pulling negatives out of the ground. So now you're negatively charged. What do negatives and positives want to do? They want to attract. If they get close enough, they want to attract so much that the air isn't enough to keep them apart. And when the air is not enough to keep them apart, that's a spark, right? So the charges that are actually being literally pulled through the air to each other, that's what makes a spark. Now, fun fact, right? That click you hear when you have a spark, you know what that is? What? Well, it makes, yeah, it makes that, but that click is thunder. That little click of a spark, that's the exact same thing that thunder is. It's just on a small scale, right? Because what happens here, right, is, and this is related to what you said, Ainsley. So what happens here, right, you got those positive and negatives, as they jump through the air, they annihilate all the air that's between them, right? It's not very much air when you're talking about a little spark, but they annihilate the air in between there. So you have it breaks those oxygen molecules apart, and you've got a little vacuum, and so you've got vacuum in that area, and air has to rush to fill the vacuum, and that's what makes the noise. Now, it turns out sometimes, so particularly if you were at the Wimhurst machine, you might have, there was a smell around the Wimhurst machine. So that is actually the smell of ozone, which is O3. So if you break a bunch of oxygen apart, sometimes instead of the oxygen coming back together as O2, they come together as O3, which is ozone. And it has a weird smell. So you might have smelled that. But the idea there is that sound of that spark, it's the same thing that thunder is. Yeah. If the Van de Graaff is positively charged, right? And you get close to it and you are attached to the ground. Remember, the ground is a reservoir of charge. Got whatever I need from it. So what's going to happen is if I'm getting close to a positive object, the positive is going to pull negative close to it. So it's going to pull negative out of the ground up to you. So okay, fair enough. So when you touch it, what's going to happen is so there's going to be that initial like exchange of charge that's the spark, and then you're going to be neutral. Yeah. Until then the Van de Graaff makes more positive charge, and then it's going to pull more negative charges. You're going to be neutral. So the moment after the spark happens, what you actually end up with is you end up neutral. You're negative before the spark happens. You're neutral once the spark happens. Right. Yeah. Yes.
If I was standing on a plastic stool,
Yeah.
right, and then I put my hand on it, that feeling I get isn't negative from the ground being sensitive, it's all of my negatives being pulled off.
Correct. So you can have what's called polarization if you're not grounded. Instead of pulling the negative off the ground, what can happen is it can push all the positive in you like down to your feet, and then so like it takes, because if you're usually neutrally charged, you've got a million positives, a million negatives, right? It pulls all the negatives closer to it and pushes the positives back down. Okay, any other questions? Since we brought it up, did somebody in here do a project on lightning? Lightning and stuff. But since we're at it, I just want to kind of talk about this in on a macro scale. So we'll talk about what happens in a lightning strike then, which again is actually this is a lightning strike. The Van de Graaff generator makes a miniature lightning strike. There's nothing different about it. But I'll just kind of, so there's my cloud. Here's my ground. Here's a tree. So how does lightning happen? Well, what happens is in the cloud during the you've got sort of ice crystals in the cloud, and then you've got water vapor. And basically, as those things turn around, the cloud actually charges itself by friction, right? So as the ice crystals pass across, like water vapor, right? The water vapor and ice crystals charge each other by friction. And I can't remember which way it happens, but I think that it happens. I'm just going to draw it as the positives on the cloud end up at the bottom of the cloud. And I haven't drawn it, but the cloud itself is neutrally charged. So all the negatives end up like at the top of the cloud. But what happens here is, again, the ground is a reservoir of charge. So what's going to happen is this cloud is going to push all the positives down deeper into the earth, and it's going to pull all the negatives up, right? And then again, what you've got is you end up with a lot of positive, a lot of negative. If you get so much positive, so much negative that they want to attract each other and they want to jump through the air, that's when you get lightning. And then the result of the lightning is you annihilate all that air, but instead of just that little volume of air that you annihilated with the Van de Graaff, you now have a huge volume of air that you've annihilated. And so when the air rushes in to fill that vacuum, that's when you get a big thunder strike. Yes. That's a good question. I'll take a minute and I'll show you, because it's interesting. I'll show you a video real quick. But all this comes from, all this can be explained by one law that we're going to call Coulomb's law. So Coulomb's law talks about the force, the electric force. Do I want to call this FE? The electric force between two charges, right? And the equation is this: FE equals K Q1 Q2 divided by R squared. What this means, so you remember what did Q stand for? Q was the charges measured in coulombs. So Q1 and Q2 are two charges, and they're going to be measured in coulombs. So coulombs, capital C is the unit for charge. This is K is a constant. It's called Coulomb's constant. It's 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. And then this would be the separation in meters. But what does this mean, right? All this equation means is that charges, like the bigger the charges are and the closer together they are, the more force they're going to exert on each other. By the way, I think your book kind of talked about this, but that looks an awful lot like what other law? Yeah, yeah. Yes, it's very similar. I'm just going to write this next to it so that you can remember. We did this last semester, right? Remember, force of gravity is G m1 m2 divided by r squared. So it's the same thing. It's a constant times, it was charges in this case, but it was mass when we were talking about gravity, divided by the separation square, right? So they're very parallel laws, right? There are two important differences. Anybody know what the differences are? Well, they're different forces, fair enough. Yes. Yeah, Emma. Gravity is weak. If you remember, this G was 6.67 times 10 to the negative 11th, right? So we're talking about 10 to the negative 11th versus 10 to the positive 9th. The electric charge is way stronger than gravity. It's actually a good thing because you know what, like the reason why our body maintains its shape, the reason why the atoms get together is because of the electric charge, right? Or the electric force. If gravity was stronger than the electric force, we would just be puddles. So electric force is way stronger than gravity. That's one thing that's different about it. What's the other thing that's different about it? You ever heard of gravity repelling anything? Gravity doesn't repel anything, right? Gravity is always attractive, but electric force can be attractive or repulsive. Questions? All right. Let me think if I want to do, I have a practice problem I'm going to do. Let me think if I want to do an easier practice problem first. Let's do an easier practice problem first. No, I'm just going to skip straight to it. So you did a practice problem with this when you did the lab, right? So you plugged in your two charges, and you plugged in your separation distance, and you were able to get a force. I'm talking about what happens when there's more than two charges. All right. So in the lab, it was station 9, right? You did so. Coulomb's law is like the only thing that's hard about it is time association, right? But Coulomb's law by itself is not particularly difficult. But Coulomb's law only works for 2 particles at a time. So the next question comes in: what happens if there's 3 particles? I'm going to start by, let's draw this out. I'm going to have 3 point charges on the x-axis. I'm going to have one at negative 0.4. One at 0 and one at 1. 1, 2, 3, 4. And this is saying Q1 is positive. Q2 is negative. Where did my blue marker go? There it is. And Q3 is negative. Now, the equation is KQ1 Q2 over R squared, right? It's not KQ1 Q2 Q3 over R squared, right? So we got to figure out how are we going to deal with this if we've got more than 2 charges. Any thoughts? Okay. You could average them. You could do that. That's going to get. That's actually not going to give us a reliable answer. Because that would give the same answer for each of the charges. Yep. Say again. Yeah, you can't do that. If you look at the units, wouldn't work out because you would have an extra Coulomb there. Yeah. Yes. What do you mean by that?
So like, you're just gonna go and do, figure out how to do it, so it's green.
So we have to find the force between, and if you're actually careful, you can do it with just two of them, but for the purposes of what I want to do, I'm going to do all three, right? So I'm going to find how there are basically three combinations of charges here, right? There's going to be a force between 1 and 2, a force between 2 and 3, and a force between 1 and 3, right? You can find all of these, right? So I'm going to say K, I'm going to write this as K Q1, Q2 divided by the R12 squared. This is going to be K Q2, Q3 divided by the R23 squared. And this is going to be K Q1, Q3 divided by the R13 squared. I ask you to try and calculate the magnitude of these. When I say magnitude, I mean, don't worry about whether it's positive or negative. Be careful when you're setting your R's. Remember, R is a separation. I did this quickly, so see what you can do with that. And if you didn't get one of those, but yeah, we're just gonna, for the moment right now, we're just gonna talk about the magnitude right now. This is it's a bunch of annoying number crunching, but conceptually so far, it's not too difficult to check, but it's just a bunch of numbers. By the way, for those of you who are interested, I put the units of the top one just to show you how the units work out if you're curious. All right, so I got 2 meters on the bottom, I got 2 meters on the top, 2 coulombs and 2 coulombs, and I'm left with newtons. And this, by the way, is why I can't do Q1, Q2, Q3, because if I did, I'd be left with a Newton Coulomb, which is not a force. So, okay, now that's not what we wanted, though, right? We needed to do this work, but it says calculate the magnitude and direction of the force on Q3. So we have to ask ourselves, what is acting on this object? So I'm going to draw, it's kind of down here, but I'm going to draw, well, let me just, for the sake of, just so that you can see it, I'm going to draw a dot here right under it representing Q3. Let's think about this. What does 2 do to 3? Does it attract it or repel it? It repels it, which means that it makes 3 go which way? Right. So what I can say is that the force between 2 and 3 makes Q3 go right. Which way will the force between 1 and 3 make 3 go? So 1 and 3 are opposites. They want to attract, which would make 3 go this way, right? So what is the net force on charge 3? Well, it would be F23 minus F13, right? And this is why, by the way, I want you to ignore negatives, right? Because we want to take care of the negatives at this point. I don't want to take care of negatives before this point. So if I look at this, right, I would say that the charge of force Q3 is F23, which is 30.78 minus 3.40. So the net force on charge Q3 is 27.38 newtons. That makes sense. Now, just because we can, I'm going to ask you to find the net force on the other 2 charges. The nice thing is all the number crunching we've already done. The only thing you got to do to find the force on the other 2 charges is do another couple 3x diagrams. I want you to see if you can. I want you to see if you can find the net force on the other 2 charges. Correct, yeah. Now, you could do it the other way, it would just mean that you could think. So it's kind of like, remember when we were doing like the loops, and we were talking about like, even if you're at the top of the loop, if both forces went down, added up, there's always the bigger force minus the smaller force. Yeah. You understand? Okay, so what we're saying here is, so let's start with this way, Q3, right? What is Q1 doing to Q3? Attracting the yes, which would mean that Q3 is being pulled left, right? So the force between 1 and 3 is pulling Q3. Yes, which would make Q3 go to the right. Yes. Yeah, so I always, one thing you can kind of do on this to think through this, right, is I like to think about when I do this, you got to be careful about drawing your diagrams, but you say, okay, 1 and 3, so if I go back to this one, 1 and 3 attract, so they go this way, right? That means that 3 goes to the left because of 1, right? 2 and 3 repel, so they go this way, they go out. That means 3 goes to the right. Okay, so that's kind of how you draw these diagrams. Yeah.
Like, I got confused when I was thinking like, because I was thinking like being pulled to the left and like so object. Would you if I'm taking off good negative? I was thinking of it as if they're both pulling it like in the Q2. I mean, if it's I have like negative S1, 2 minus.
Sure. Yeah, that works. Yeah. So what you would say is, so you basically got negative 74.662. Yeah, you can do it that way. So you just have to think through what that means. In your method, everything that was left is always going to be negative. So whether or not it's going to the right or left depends on whether your answer comes out positive or negative. I
Take the sign off, specify that it's going left.
Yeah. I mean, that's how you would remove all, ambiguity from that. And that's kind of actually what I ended up doing. I didn't do it when I did the first one, but if you look at it right, this one ends up going to the right, that ends up going to the left, that ends up going to the right. So again, you are now capable of doing that first section on the syllabus. So I'm going to give you some time to do that. You know what? I can, if you would like, I can open test corrector, but I can open it while you're in here, but I don't want to open up for everyone. But if you want, I'll also open up test corrector so you can do that while you're in.